There's so much we can do. Like simple simulation and the Vention platform can go so far. There's so many quick wins. That's why, going to fetch the data, but I agree with you 100% that this is a competitive edge. Yeah.
We don't have jobs. We're just out here throwing out ideas. You have a job. So, you actually have to think about what you have to do. But yeah.
Welcome to the Darby Mill series, Intrepid Pioneers of the Next Economy, featuring discussions with entrepreneurs at the forefront of deploying machine intelligence and brainstorming sessions about where the technology may go at the limit.
Welcome back to the Darby Mill series, Intrepid Pioneers of the Next Economy. This is our first episode of Season 2, and we're here with my three collaborators, Rich Sutton of the University of Alberta, who pioneered reinforcement learning, Sendhil Mullainathan of MIT, who uses machine learning to better understand human decision-making, and Niamh Gavin, applied AI scientist working on optimizing foundation models. Rich, Sendhil, and Niamh are all senior advisors at Intrepid Growth Partners. And the domain that we are going to explore in this episode is automating manufacturing. Just like in episode 1 of our first season, where we focused on automating factories. The company we're going to be meeting with is Vention. They're headquartered in Montreal. And with us today is Etienne and Francois. Etienne's the founder and CEO of Vention, and Francois, the CTO. I've had the pleasure of visiting their headquarters. They have two significant buildings, one in the downtown and one near the airport. They are, their mission is automating factories, and part of what the way they do it, they are very economics oriented. So they're very focused when they do their work on what is the payback period for the customer. How fast will they earn back whatever they're investing in their Vention product. And they are somewhere at the moment, between a year and a half in terms of payback periods for most of their clients. And they have some big clients, customers like Tesla and Amazon and L'Oreal, Lockheed Martin. They're doing real factory automation. I gave you those big brand names. They're also doing work for much smaller factories that because their methodology is reasonably low cost, it's affordable for smaller companies. And so, given all the commotion these days about reshoring manufacturing, that this is a very timely topic. And I don't know, Rich and even Sendhil, if you remember, but we kicked off season 1. Our very first session was on automating factories, and so here we are automating factories this time with Vention. So we'll start off just with a video, and what you're going to see we're going to talk about two applications of AI here. The first one is in the design. So customer comes and they says, they want to automate this part of their factory. And what's one of the key innovations by Vention is that they have effectively a wide range of parts in their catalog that all fit together. So it's like, they describe it like Lego. And so as you're assembling your machinery, they've got an AI that's effectively like a recommendation engine that is predicting what's the best next part for this piece. So we can play this here, maybe with the volume down, and what you'll see on the left hand side, you may have watched this already, on the left hand side, in the left column under design and programming, that as the person mouses over, it is recommending which part to put there. And Etienne, I should turn it to you to give a little more description of why this is so powerful for your clients.
Yeah, and it started with an understanding, Ajay, of how manufacturing assets on manufacturing floors are made. And today, most manufacturing assets are unique because the finished good is unique. Only Nike manufactured the Nike Air, and only Hershey manufactured the Twizzlers. And as a result, they have unique machine. And to create those machines today, you need a lot of expertise. We refer to them as system integrator. And that expertise has a price. And it had roughly 40 to 50% of costs to the capital expenditure to automate. So it makes automation, in a lot of cases, not profitable. There's just too much capex to absorb. Payback is bad. And that was the problem to solve. And if you look at the approach we took was to Legoify, you alluded to that, but we've platform automation to remove a lot of the human content required to create those systems. And one way to achieve that is obviously with AI. when you design a machine, there's thousands and thousands of components that you have to pick and choose from all the vendors, and you need to make sure they're compatible. And obviously, if you can have an AI that help with this, like in the example you've shown, you can save just a tremendous amount of time and at the same time reduce tremendous amount of cost. So that was the and there's Vention is much broader than this, but if you constrain your question to the element of design, I think this is an opportunity to bring AI to really speed up the creation of those custom manufacturing assets.
So now what you're seeing is moving on from using machine intelligence for design. Now there's some part of your either manufacturing or assembly process where you might have had a person doing a thing, like in this case, picking up a part and placing it on a conveyor belt. And so when you're designing your automated factory on the Vention platform, in addition to the parts that we just saw on the in the previous screen, you can put a robotic arm into your assembly. And so here they're showing a robotic arm, and the other application of machine intelligence is effectively as a control system to move this arm to do the task. And so here it's doing this sort of reasonably simple pick and place task. And the key is that you can get an arm. So just as you're assembling your factory, you can drop in an arm with a particular end effector. In this case, it's a gripper. And then with a control system that allows that gripper with very little training, additional training, to do this task. So we can continue playing this video, and Etienne, you can provide a voiceover here.
So we kept a very pragmatic approach going into control system where if you walk a factory today, you have all those fixed operator. They stand in front of a machine, taking part out of bin, out of tray, out of the conveyors, and placing them in another machine for a subsequent manufacturing operation. And those type of tasks today are automatable with the same hardware that we know, but they do need the kind of frontiers AI model in order to do perception, grasping, and real-time path planning. So that was the demo we were just looking at, where we start to combine those kind of modular design with proper AI or physical AI. You can start to have almost the best of both worlds, the speed of integration and design with obviously the ability to tackle those unstructured tasks that are not automatable without AI.
And just Etienne, this is the today versus tomorrow, which is going to be a springboard for our what happens at the limit conversation. But in this image, what you are talking about is how the process is both becoming faster and cheaper. And so, can you explain to the listeners just the kind of at a high level these key elements? Why is automating a factory becoming so much faster to do and cheaper to implement?
And this is sometimes a controversial topics that I talk about when I'm in front of like practitioner from the industry. But I always say the robot cells of tomorrow will cost less than the robot cells of today. Right? In a world where robots are powered by machine learning models, you no longer need a PLC, you need GPUs.
Just for listeners who don't know what a PLC is, can you just describe the difference?
Yeah, it's a programmable logic controller that monitor multiple states of a given machine to orchestrate is various movement. But it's a traditional way to program machine with almost a real-time behavior. They're powerful, and today they could be considered the center of the robot cell, but this is about to shift as now what's becoming the center is physical AI. So if you think about a traditional robot cell today, you need hundreds of sensors to orchestrate the various movement. Tomorrow, we'll have what we call the bazooka sensor, a camera, maybe one or two in a worldview, where you can orchestrate the same behaviors with a much more simpler device that costs less. Today, you need jig and fixtures to present the part in a very precise orientation to the robot. Tomorrow, because you have camera, you can deal with unstructured behavior. So again, you no longer need jigs and fixtures. That costs less. Right, so if you start to adding those up, and you can even play with the robot arm today to have a very precise robot, you have encoders in every single joint. And the feedback loop into the robot is encoder based. Eventually, and we see this already in academic research where those robot gets much cheaper because you're using the camera to drive the feedback loop. So the robot arm will also get cheaper. So if you start adding all this up, what we see is the robot cells is shifting from a hardware to software, but the price will also go down. And as a result, more stuff will be automatable profitably. So I wouldn't tell you with a precise time estimate if it's going to take 3 more years or 5 more years, but I think the underlying trends are well underway.
Excellent. Okay, Etienne, thank you. I will just begin by opening it first to Rich, then Niamh, then Sendhil. They have any clarification questions, and then we'll switch gears and move on to where does this all go at the limit. Rich, any questions on your side?
I think I read something like 4,000 customers, and I just wanted to. I was just impressed by that, and I was wondered if you could shed a little bit more light on what the current customers are like, what you're doing for them.
Yeah. And it is an impressive number. And I think it's mostly speak to the fact that when you make industrial automation very simple and you provide some level of self-serve tools, practitioners in factory floor are able to do great things by themselves. And this has enabled us to reach a very wide audience of manufacturing professional since the founding of Vention. So today the business is roughly 40% enterprise grade with some of the larger logo that Jay mentioned, and 60% remain those small, medium businesses up to mid-market that are automating using the Vention platform. But it was the benefit of having two go-to-market motion, this kind of product-led growth, inbound driven. And as the platform got more mature and more robust, having this more traditional top-down enterprise sales-led motion that enabled us to develop some of the logo Ajay referred to.
That's impressive, and congrats, guys. I think this is a wonderful practical application of the generalizability of Gen AI. I had kind of two quick clarifying questions, if I may. One was going back to the start where it all began. You mentioned in the video that you had a data set of around 400,000 label designs that the model's working off. And I was just wondering where you got that from and how important that was to the start. And then the second one was then around on the hardware side. You referred to the GPU over the PLC. Is that model running locally? And if you're leveraging the out-of-the-box turnkey NVIDIA solution, does it capture your specific loops to feed into your own model, or is it feeding into a general model that everyone's benefiting from, and how do you think about that?
Yeah, I'll split the answer with Francois, our CTO, who's on the line. So I'll take the first question. I'll give the second one to Francois. But let me talk about where the data come from. And I would say it's a little bit of luck and a little bit of a good instinct as we've built the business model, because we decided to Legoify the entire act of industrial automation with 3,000 Lego parts. From the get-go, we've built our design graph in such a way that we could then learn from it in the future. And because we work with prescriptive geometry or predefined geometry as opposed to free-form geometry like most 3D CAD software, we ended up with a very rich graph or design graph, right? A part has a function, has a description, has a name, has a weight, has a supplier, has a lead time, has many orientation options with various connectors. So there's a lot to learn from a single part in that prescriptive environment. So I think we were clever to instrument the business model the right way. So eventually we can run machine learning on this. And a little bit of luck because Vention was probably the first cloud-based industrial automation platform starting in 2016, 2017, and we got amazing traction. So you combine the two, and today we sit on a pretty large data set that include a lot of design data, a decent amount of programming data as well, because users in Vention either program code free or in Python, and more operating data now that those designs are getting deployed as well. Now, I think what we're doing with all of this is we're barely scratching the surface, and by scratching the surface, I think maybe we're, I'm not even can call this a scratch because we're so in the early days there. Perhaps I give the microphone to Francois to talk about all the benefit of that.
Thank you, Niamh, for the question. So just to make sure I understood it well, your question was around running the models on-premise locally or in the cloud, and if we were using foundation models that were different from others. Is that correct?
Yes, just exactly as Etienne was kind of saying, you want to benefit from every time it runs locally, but then do you also benefit from all the other users around the world by feeding into a single model, or have you gone for a custom local model that's proprietary?
So we do a hybrid approach. So in terms of running in the cloud and running on premise, if I can start with that, there are certain things that absolutely have to run locally on premise, and that is the machines when they are operating in the factory. Customers sometimes don't have a stable connection, or the network will drop. Things need to continue to run, right? So we have equipped machine motion AI with enough GPU and compute locally to run the models. Now, there's also tasks that don't need to run locally. For example, when we utilize AI pipelines for a design system, so to build in Machine Builder, or to leverage simulation for things like grass planning. So grass planning is, a strategy that we utilize to do simulations in a loop and utilize RL to determine which grass for a certain gripper will result in a successful pick. So we test it with physics, but this is going to go sub-real time, super accelerated, that runs in the cloud, right? It only is a preliminary step towards being deployed on a real machine. So we really have these two approaches. Some stuff is accelerated, sub-real time, or can run while the user is designing. That goes in pile, but some things are used to control the machine, for critical applications that runs locally. So that's for the first question. The second question, and I said we're using a hybrid approach because certain models are absolutely incredibly generalizable, and for us, there's very little value in investing more in the data of these models. But for certain things like, for example, grass planning, there is value to invest. So we do a bit of a hybrid approach where we're going to ingest a little bit more effort in building our own models and gathering more data for a certain element of our pipelines. And for certain areas like pose estimation or segmentation, we utilize tools that are going to be provided by the big guys out there, the NVIDIAs and the Metas. And then the magic for us is how we put all of this together. Hardware that works and is easily to deploy, a workflow that we can stitch from end to end. And then we put all the models together, and then we create the outcome. So does that answer your question? Is that
Terrific. Thank you very much.
yeah? Okay, good. Thank you.
Excellent. All right. And to Sendhil.
I love what you're doing. Super interesting. I guess part of what will help me understand it a bit better is I just have some questions about potential products that you could build that I think build off of the scaffolding you have, and possibly you haven't built them already. And so I just want to understand, that'll give me a sense of what you can do. So one thing I could imagine is, even if I just take the original, the thing on the left, today's architecture, where you're helping someone design a machine that says, hey, for this thing, this part could be useful. This is a good part to use over here. This is, it was kind of like an incredibly useful thing to be able to go through the entire universe of ways to put this thing together and think through what are some ways of putting it together. When that's running at scale, I would have thought you're also now generating really interesting potential insights. Let me do it from level up. The lowest level would be, here's a kind of part that it looks like across a bunch of things would have some really high demand. The next level up would be the equivalent of, I know nothing about manufacturing, so what I'm about to say is like utterly made up. You can tell me this was really, really wrong, but the equivalent of someone saying, we only have nails, but here's a whole new kind of fastener, screws. I know screws are from 400 BC, but whatever. Like, here's a whole new kind of fastener that we don't even have on the thing. But if someone could invent a fastener with these properties, so that's one level above saying, here's a small deviation that one could build something with these tensile strength, but here's a place where innovation would be really valuable to a lot of people. So even just sitting on the left, I guess I'm trying to understand, it seems like you don't just have a window into satisfying needs today, but the inverse of that window into satisfying needs today is to understand what are the bigger unmet needs that are torquing designs and would have really high value. Is that a kind of thing that you could use? Imagine you at an even bigger scale, or maybe already at the scale you have. Is that a kind of thing that the platform could do?
You want to take this one, Francois? You want me to jump in?
I'm trying to understand. I understand part of your question, Sendhil, but I'm not sure I understand it fully. You're looking for unmet or things that are a little bit outside the box of the exact problems we're solving, something a little bit extrapolated in the future. Is that right?
Let's suppose that I'm assembling something. I don't do manufacturing. I do bookshelves. I'm putting together a bookshelf. You help me put together a bookshelf. And in the process, given the stuff out there, you say this would be a really good thing at the bottom that would hold the shelf up, and that's fine. And we'll go through that. But helping many, many people assemble bookshelves, your model actually has some implicit understanding that there's a kind of fastener that lots of people would actually really value, but is undersupplied in the market. So in a way, you're almost, it seems to me like you have the data to start asking, what is the demand the market of equipment is not filling, but which there are big demand?
I
Does that make
understand.
any
Yeah,
sense?
yeah, yeah, it does,
And
it
then
does, it does, it
meant
does.
by the different levels is you could imagine currently a lot of the factorization of even how we start thinking about the pieces depends on the pieces we have. But you said, what would be a very different factorization if I could just have one new kind of piece? That's further out. This is
Yeah.
me just using the current factorization. But I guess that's my question. It feels like by virtue of helping people build their stuff, you're also answering implicitly the question, what stuff is out there that would help builders the most? If that makes sense.
So basically, yeah. So basically, you're saying, we are going to provide so many machines to the field with our components that we're gonna know what's the best, basically, catalog of parts and where are the holes in the market. Um, and one thing, yeah, one thing we've seen if we look at the past, because not looking, I don't have a genius idea just yet to answer the question, but if we look at software-defined safety, safety is a pain. Like you don't even know, but it's so important, right? It's like you don't want anybody to get hurt, and it's critical that you have it, but it's always an afterthought. And we've seen throughout the years that having software defined safety, it would be something extremely powerful and something that is very vitally simple and can be only software defined and make sure the machine is safe. And we're seeing the
Fantastic.
emergence of these NVIDIA is thinking about some of these things and new technology for this. You deploy a machine, you put cameras around in the vicinity of the machine. It has safety rated software, and then you can after the fact configure the software and it will stop your machine and then make it safe. No light curtains, no special safety rated sensors, no interlocks. We see this. It's hard to do. If we had that magic safety component, we would do a lot more. I'm not sure who's going to do it, but we see some of these elements. We've seen some of these elements in the past.
And I guess part of what I'm almost asking is, you could imagine, let me give a dumb example. Screws come in these lengths. So when you suggest them, you suggest a certain length. Looking across all your things, your algorithm might say, if there was a length in between these two, boy, would that have a lot of demand, but no one is producing. I mean, there's sort of an automated search you could almost use the Gen AI capacity for, which is to generate new parts and ask what new part would your model have made the most calls to, and kind of play that game a bit.
We're doing kind of I would say a manual version of that today, but that will echo your point, Sendhil, in the sense that very often we see a client playing with the constraint library that we have today, right? And they benefit from the speed and the ease of use, but we see those emerging needs slowly popping up, right? Like a couple years ago, we were not involved at all in robotic sending, but we saw client over and over trying to design robotic sending cell. And today we've productized a little bit that piece of the application, and we have to create new component for this. So we're doing this, as I would say, in a manual version. But there's enough demand data, there's enough demand data on Vention that it could be, we have a great opportunity to put an AI tool to surface those needs a bit more explicitly across all the data that we have, whether it's the 3D design graph, whether it's the specification that people have entered, whether it's the code that people have entered on those machines.
And the automation is relatively fragmented in terms of execution, right? It's integrators and really in regions and in like areas. They have a confined area in which they operate. So it's rare that you have one platform on which the entire world converges to in automation. And I think this is a bit of a strength of Vention and why this idea makes sense, right? Like you kind of have like an ultimate automation product survey in one place, and this is why we have the 4,000 customers as well, right? It's the way Etienne wanted to build Vention was cloud first, digital first, so we bring everybody in that same environment And then we have this convergence of people in Minnesota building a machine, people in Japan building a machine, coming together.
And is like an example of a manufacturer for you, like Bosch? Are they a manufacturer that would have parts that would supply to your people? I'm trying to think of a name of company.
You want to take that one, Etienne?
So on the Vention ecosystem, right now there's 3,000 Lego parts. 2,000 actually carry the Vention brand. We had to create that kind of Lego-like architecture, and 1,000 are from our marketplace partners with name brand that like Dorner Conveyors and SMC. But in all case, we've kind of make sure that everybody shared the same mechanical and electrical architecture, so everything that is available is compatible. And once you have that kind of base foundation, the AI on top can really do more things, because it really simplifies the problem. So the benefit is it's super fast. There's no more integration left on the factory floor, and therefore it's much cheaper. The cons is you need to work within the ecosystem. So you need to see Vention as an Apple-like ecosystem that is semi-open or semi-closed, and you reap the benefit of AI within that construct or that sandbox.
So then I guess in that context, this is my last question. I'll just move on. Is that it strikes me that it would be very, very interesting. Like if I was thinking, you have one path, keep most of the products home built. The other path is you're like the app store and you're trying to get Bosch and all these people on. I would have thought that one interesting thing about getting someone like Bosch on is even before you have a lot of demand on one side, if you say by virtue of being on this platform, we can give you insights about what your next level of parts needs to be, that would strike me if I were Bosch would be super valuable to me. Like even well before you have any number of customers, it's like, yeah, this is one place where if I get on, sure, it's 3,000 customers, which for Bosch may not be as much as, but boy, these guys. So I would almost ask, what is the product for Bosch above and beyond having access to your customers? And I just listed one, but maybe there are other products that they would find valuable because you're sort of at the heart of a hard problem.
Your intuition is entirely right, Sendhil. So the question we have for us is, at what scale do we build those products versus all the other product that we need to invest into, right? Because there's just so many things to build. And physical AI or AI was something that was on nobody's radar just 3.5 years ago. And it had a decent amount of R&D investment that we're making in that arena that compete against other priorities. But your intuition is exactly how we think about the business.
So it's probably obvious to everyone, but just in case, when you're looking at the blue infrastructure on the screen, it's not that they just do the design on the Vention platform. Then there is an assembly facility in one in Canada and one in Europe. All the parts are taken out, they're put on a pallet, and then they're shipped to the customer. And then they are, they assemble on site. So this is, in other words, it's not just software. There's huge warehouses with all this stuff there. And I mentioned two applications of machine intelligence. One for enhancing the design process, is effectively, predicting next best part when you're putting your thing together, and then also the AI as a control system for the robotic arms. But there's another one that I didn't mention, which Sendhil had already started zooming in on, which is because people are designing their stuff on the platform, they have information for demand forecasting of parts that their competitors don't have. So all the traditional companies in this sector don't get the benefit of seeing the early thinking and planning of their customers who aren't doing the design on their platform. So that generates valuable information. So what we're here talking about then, when we're talking about the when we did season 1, episode 1, we were focused on effectively what kind of intelligence could we get by putting some cameras, some sensors retrofitted onto existing facilities. Here we're talking, now we have in some sense the luxury of conceiving of an idea, designing it, and implementing it. And then of course, Rich will be interested in, once it's implemented, its ability to continuously learn and improve while it's on the factory floor. And then, given that it's learning and improving on the factory floor, how does that influence the upstream process of design of other stuff, and ultimately, the design and the forecasting of parts for those design and all of that. So let's shift gears here and talk about this. Like, where does this, take us? If we're in a world now where especially in Western countries, an increased interest in manufacturing. And now with platforms like Vention's being able to go right from zero to automated, designing an automated facility quite quickly and reasonably cheaply, Etienne's given us, this is how it looks today. Sendhil's already started trying to think about, wait a minute, where could this go? Rich, we'll start with you and then go to Niamh and Sendhil in terms of taking it to the limit.
Very good. I may have to ask one more question, or maybe we'll just start going. And if we're thinking about the limit, we need to know more about the interface between you and the customer. I mean, I'm guessing the customer comes to you with something they want to assemble. Here's something they want to assemble, and then you come up with the automation design and provide them one of these layouts as in these pictures. But then the thing has to be run. It has to actually run, and that's going to run in their factory. And who's going to run it? Who's going to run it? Because lots of new problems will arise when you run it and make sure that it works properly. So I wonder this boundary between your guy as a facilitator of a manufacturer's automation and the manufacturer who's doing the automation.
But there's one thing that's a little bit special here, Rich, that I think is important to note. Is ideally it doesn't need to really run.
Ideally, it'll run exactly as it was designed. Is that what you mean?
Exactly. But I'm trying to hint at simulation. I think this is a super important element here in this conversation of reinforcement learning and AI and automating automation, right? Like, I think we want to get into a world where we don't have to really run the machine before we know it works. But to answer your question about the interface, maybe I start by answering this one. The customers will come on our website, and we have a tool called Machine Project. They dump their specs. They talk to us over the chat, and they tell us their intent. I want to sort tomatoes. The green ones go to the left, the red ones go to the right, and my machine needs to be 20 foot long by 30 foot wide maximum, and it needs to cost $100,000, and hopefully it also makes me a coffee in the morning, right? And then we work with them to determine what are the right specs. We assemble them, or we create it for them in our virtual environment. Sometimes they even take a crack at it themselves. Some are very successful on their own. Sometimes we help them. And after we simulate the machine, we program it. Okay, if you detect a red tomato this side, a green tomato the other side, and then after we run it into our simulation tool, and then we see it in action, and we determine go, no go. In a nutshell, right? I'm super simplifying the flow.
So there's already a lot of customer data that is either explicit in a spec captured on the Vention website, or implicit that we need to ask the right question over a call to capture all of this and translate that into a 3D design. And to your point, Rich, that 3D design is just the mechanical. Unfortunately, it's not smart yet or intelligent by any mean. And the next step is obviously to program that logic. Now, because we have all that data set that is fully labeled and structured, the frontier is to put an AI agent, to do that work, as opposed to humans, puppeting the work from one step to the next. And today, with the design tool, for example, we're very good at predicting one or two parts in a mechanical context. So if you mouse over a given mechanical context where there's multiple parts intersecting, we'll be able to solve that situation and provide the right part, or for that mechanical context. But we're not yet able to say, just put in a prompt the tomato example that Francois explained, and get the entire machine being built by itself. So that's, to me, where we're here today is you can predict 2-3 parts based on mechanical context. There's enough data to do that well with AI. But to have the fully prompt-based design for a spec base of industrial automation, we're not there yet. But that's the exciting journey in between, right?
Yeah, I heard limits, so I thought I would go there.
Okay, so then if we take it to the limit, you provide a tool to the customer, and they use it to design the thing they want assembled, because you don't just participate in that design process. And then once they reach a design they're happy with, they send it to you, and you do your simulation and figure out a way to assemble it. And simulation works totally reliably.
It's actually even more, a little bit more self-serve than this, Rich, right? People go online, they design their machine, and when they're happy with the mechanical design of it, they program and simulate very often by themselves in the same environment. And that means they can validate stuff like cycle time, right? And get a sense of payback. Once you have cycle time and throughput, then you know your payback, and then they can decide to purchase it. And that's where Rich will, and we should do the experiment. We'll send you a big IKEA box full of Vention with that machine and with your little booklet, your little assembly instruction that were also generated by AI, because you need to parse the design and figure out what their logical grouping of assembly step. People assemble their machine, and now it's time, to Ajay's point, earlier point, now it's that where we shift to control, because that simulation you created in the cloud, that digital twin, needs to become the physical twin. So that simulation needs to move from the cloud to the edge controller to start operating the machine. But the frontiers is making sure that everything that was de-risked in the cloud from a process perspective, making sure at 99.999% we've de-risked the yellow from the green from the red tomato, translate on the factory floor without having to invest all those integration hours. And industrial automation is such of a long tail industry. It's hard. And there's just as much technology risk, components don't fit with one another, as process risk. Oh, we thought we would be able to achieve that, first pick yield, and it's actually much lower. And as a result, it doesn't scale to industrial grade. So those are the two risks. To eliminate technology risk, we're able to do that with Lego parts and a mechanical and electrical architecture. That's what we did. Eliminating process risk can only be done with very accurate physics-based simulation. And that defined another frontier. So we've made good headway there, but I always say there's more to build forward than what we've built behind. There's more to build forward there.
Okay, so there's really an extensive process with the customer designing iteratively, trying things, looking at how to assemble it, and then presumably there's, that is, they really become the customer when they have something that they fiddled with and think and then are happy with, and then they decide to make the investment of actually buying the setup and everything. So the kicking to the limit, you would provide all these tools, they would play around, figure everything out, and then you would step in at the point of producing the thing. You do some additional checks, and you deliver what they have figured out. They're doing the figuring out and customizing to their particular factory, to their particular needs. I was worried about how it would interface with everything else that they have, but they'll be figuring that out.
But I'm not sure that's the limit, Rich. I think the limit is the customer doesn't do anything. We don't want them to do very much, right? I think the limit is, if we think AI or reinforcement learning, there's two feedback signals or reward feedback signals we have in our system. It's customer feedback and it's simulation feedback. So let's say we can extract, with these reward signals, 100% of the information we need to go from intent to a machine that works. This is the limit. The limit is a customer goes on our platform, interface, and I'm talking limit, right? This is very futuristic looking, but because we have the entire architecture and we have the entire end-to-end platform, and we can actually automate, the creation of the workflows, and you can build these reward signals to be very strong, and we control everything, right? Design, programming, simulation, the parts that go in the platform, and what ships to the customer. The customer comes in, they say, I want a machine to sort tomatoes. Here are my specifications. A machine gets generated, simulated in the back end, then presented to the customer. The customer says, oh, no, actually, I forgot to tell you, this machine is too high. It needs to be 5 foot tall to maximum. And then feedback with the simulation. The throughput, actually, it's too expensive. Diminish the throughput by removing a robot. The AI keeps working, simulates, builds, simulates, build, simulates, build. And at the end, okay, perfect. The customer has the machine, parts get shipped, machine gets assembled, machine gets deployed, it works. This is the limit, I believe.
And Alphabet has 26 letters. Vention has 3,000 Lego parts to play with to solve those problems, right? So that's a little bit how we see it.
And I think it's, this is in many years, but each section of AI we've started to inject in the platform is, an agent in that workflow that will bring us to the limit. A co-pilot agent for Python programming to program the machine, an assistant to help you in Machine Builder to build faster, some automatic motion planning on the edge so you don't have to pick up every waypoint. Then it progressively, all of this comes together to automating automation, basically.
The tagline, automating automation.
I like that vision. It's moving much more towards the customer providing the specification or the goals, but you iterate at the goal level.
Yeah, and you automate faster than real time is also the other very important aspect, right? If you can simulate faster than real time, you can also do a lot more than you can do in a minute of a person, which I think is also another element that is important in this story.
All right, we'll move to Niamh.
I'd love to expand upon or just re-emphasize what you said, AJ, about what I think is quite unique here is that you have this holistic end-to-end platform in the truest sense, from design to deploy plus customer support. So you actually have this closed loop feedback system that most aspire to eventually get to from the start. And it is this beautiful RL environment in the truest sense of this ultimate feedback loop. And then on top of that, because you're designing the Lego bricks, you've made it, there's inbuilt modularity and customizability within it, such that you can actually optimize every single element of it and that have that compounding effect towards the limit, which is quite phenomenal. I've never seen that truly in the end-to-end sense beyond kind of marketing aspirations. So that's really interesting. And then, as you say, we've gotten to the point too where it's not just software, hardware, but the models, the vision, the end-to-end, the natural language interface that we're moving towards. This really is an actual sandbox for Rich to play in the real world that I think he's always wanted to have. And I imagine it can even get to the point where you see where the most common failure points are, and to say, for example, the particular gripper that comes out of the box struggles on this curved Lego bit more than any other. And then you can decide, okay, should we change that Lego brick or should we change the gripper and optimize it from it? So I find that really interesting. And then on top of it, because you've got this app store play, and as you said, you've got kind of product-led growth, if every time you almost let the customer or the end users build out your platform too, because when they've come up with a design that is for a common use case or even a long tail one, they can upload that, and then others can click on it and order the turnkey solution for that too. The question is a little bit what Sendhil was leading towards. Have there been any surprises here or little nudges that you've made in that variation that have had huge uplift? Like, I don't know, everything to date has been a square corner, and that's actually really difficult for a conveyor belt. And because you're building a Lego brick, you've made it curved, and that has increased speed and effectiveness. Are there any learnings like that you can share with us, just out of interest?
There's so many, but I'll go back in 2017. So that's almost pre kind of mainstream AI. I was wondering if people would accept to design outside of SolidWorks, which was the default standard to design those machines in a full free-form fashion. We were wondering, would people accept to assemble their own machine? Because if they don't, there's no business model to build. It's not scalable otherwise. Right. So we go back, and I remember in 2017, we had those kind of 10 hypotheses. If one of the 10 is true, there's no business model. Right. So we spent a lot of time de-risking every single one of them. But I'd like to say manufacturing automation is a very long tail industry. And it's probably the best defendable moat that there is, because it's really, really hard to generalize. And we took a product, hardware, and software approach to generalize industrial automation. And I think today we're still believer that it's not possible to generalize industrial automation without tackling the hardware part. And maybe in the future we'll be there, but I don't think we would have had the growth we would have had otherwise. But today now, what's the beauty is that foundation that we've built, that Lego kit, that designer, programmer, simulator deployment is still even more relevant in the context of AI, because it created all the foundation, all the data set that we need to then automate the workflow. If you want to automate automation, you need that initial foundation. You don't really have a choice. There's no shortcut there. So I'm very excited for what's ahead, I guess, from that perspective.
Sendhil, over to you.
Yeah, I think I'm going to be going back a little bit to Rich's question, and I just to set the stage to make sure I'm on the same page. It feels like the way you said it, Etienne, is that there's sort of two problems. There's sort of the process optimization problem, but then there's actually the parts problem, and the parts problem is overlooked, and you guys kind of really nailed that, which makes total sense to me. But since we're looking into the future, I want to just think a little bit about the process optimization problem, and I want to talk about the tomato example Francois kind of raised, which is I think there's two aspects to the tomato problem. One aspect is close to vibe coding, which is I say what I want and write code that does it.
Yeah, but build a machine and writes the code that does it.
Yeah, and do the whole thing. Yeah.
Sorry.
And I think that makes sense. I think that part's less interesting than a different part. The different part is, I think, what you also meant when you talked about which is what you meant most when you talked about process optimization. So let me just make a very concrete example. Let's say that I think I saw on your website that like bin picking was one of your kind of categories of things people could be building. You're trying to build something, I'll pick something out of a bin. And suppose I'm building a bin picker. And there's a bunch of questions about details about parts to use, how to use, which part to use. I appreciate physics simulations, but I think Rich, in his nice paper on sort of Welcome to the Era of Experience, he sort of talks about ages of data. And the first stage of that data is sort of simulation data, which is great. But simulation data is limited by the quality of the simulator.
Exactly.
If you kind of think of bin picking, it's pretty unreasonable to imagine we'll ever reach the point where we'll have a good enough physics simulator to simulate the objects I'm picking out of the bin to understand which things can be clutched and dropped. It just feels,
Agree.
it just doesn't feel reasonable. So let's just stay on bin pickers and assume we don't have simulators because it's then I think we'd sort of come to the era of experience where we'd say, look, we have lots of customers, many of them order bin pickers. This sort of transformative future end at the limit, what is the minimal thing we'd need? We'd need data flow back from the customers on key process things. Like a key process thing could be how many things are dropped or how often does the hand need to pick something up. So even in this utterly trivial example, if that information were flowing back, then it would seem to me like you could start asking questions like, is there a very tiny model we can build that can be learned, automatically learned, RL'd, that would start to give us a sense of, here, tell us what you're picking, take photos of it, show us whatever the medium we decide. We then think we can use the experience from other people who have built bin pickers to automatically suggest things that wouldn't just amongst the space of things that would all do a pretty good job picking picking from the bin, we think we can then start to tell you this kind of arm will work better for this and for this reason. And so we're sort of letting the community do collectively RL together at some level is what we're kind of doing. And that seems utterly doable from your point of view, because instead of trying to boil the entire make the process good, which just feels crazy, you just could start with like one or two parameters that you think are key. And if you can collect that outcome data, and that's automatically flowing back, you now have like your design thing goes from designing a thing that works to designing a thing that works and does well on this dimension that none of us have a way to think about. And then you can sort of expand the dimensions. Does that feel like a kind of thing that would be in the feasible set? In the future, in the limit. I don't know what Ajay means by the limit, but it's all in the future.
Yeah. So one comment is, I think there's also a certain proportion of Vention's focus that is on my definition of at the limit is very far, but perhaps still for entry to medium complexity automation where for example, the bin picking requirements are not going to be so super advanced, right? So because I think you are correct to say that there are some elements of bin picking intralogistics, for example, what Amazon is doing, the variety and just the search space and the state space is so wide, it's very difficult, right? So I think that one of the advantages of Vention is that, we do complex machines, but our target is more what hasn't been automated in the past. And very often these things are the tail of automation, and the SKU mix is not going to be crazy. We're going to have like 10, 15 SKUs. As long as we can upload them on the platform fast, we're happy, right? But if we go at the limit in terms of SKU and variety, I think your point is valid that things get extremely, extremely varied. Then we are going to need some level of sophistication how we train, which can only be addressed with real data from the field. And it's absolutely possible. I mean, most of our machines now that ship our latest generation controllers connected via LTE, we get the data back from the field, and we can start, if the customer can, accepts, of course, we can start to use this data to refine.
As a business point here, Sendhil, is that enabling what you're proposing is that, if you're the customer, for example, you can choose between a number of different robotic arm providers. Now the end customer is interacting with Vention as the data, in terms of those data flows, not the arm producer. So like the customer relationship is with Vention, and that data loop is with Vention.
Yeah, and I think, Ajay, that's exactly, and that's why I was pushing a little bit, Francois, in that I actually wonder if it's in your sort of competitive advantage to not be in the places where physics simulations work. Because in a way,
Yeah, I understand what you mean. In a way, we have an edge to get the data. You
you
don't.
have an
Yeah,
edge.
yeah.
Exactly right.
But we're definitely
Exactly.
in a space where we can leverage physics simulation and generate more dollar
Without
out,
question.
out of a sim.
No question you should do that. Sorry, I'm not saying you
Yeah,
shouldn't, but
no,
I'm saying everyone can, in principle do that. You can do the next thing that almost no one else is positioned to do.
we have very valuable data, which maybe clutters my vision a little bit because there's so much we can do. Like simple simulation and the Vention platform can go so far. There's so many quick wins. That's why, going to fetch the data,
Yeah.
But I agree with you 100% that this is a competitive edge. Yeah.
We don't have jobs. We're just out here throwing out ideas. You have a job. So, you actually have to think about what you have to do. But yeah.
But those little details, like Francois mentioned, making sure that every machine going at the shop floor is connected. And if you want to have machine connected, you cannot leverage the plant Wi-Fi. Nobody will let you. So you need to have cellular connectivity out of the box, right? Making sure that every machine that goes in the field is fully instrumented. If you want to have a deep instrumentation, you have to build a little bit of hardware there, so you can track what's going on in the actuators, and right, you can have that data bring back up to the cloud eventually. So we when I talk about being luck and clever, this is on the clever side. We've made sure that this end-to-end ecosystem will allow it. And I love your example, Lee. This will become a massive reinforcing loop, right? From the specification definition to design to deployment on the field with all the operating data feeding back in.
And the portion with data gathering from the field that I feel a little bit uneasy about is the fact that when you train models, it's essentially a big design of experiment, a big black box that you fill with a billion parameters, and hope things will work out. And very often they do. But the problem is, as soon as you change the system a little bit, then that model is no longer that good. It might actually be completely off. So if you train on data that is hardware specific, a certain gripper or a certain machine, a certain friction, it doesn't mean that this data is going to generalize well to other types of machines. So it's very delicate. If I think the data, we gather it, we have access to it, we should keep it. It will be useful, but it's just not so automatically useful.
I'll make a technical point, because I think the reason I wanted to give it at this level of difference between the physics and whatever is, Rich and Niamh, you can correct me, but in the stuff at least that we've been doing, one of the things we found is there's sort of one extreme, which is just treat the data as data and just black box model it. Then there's the other extreme, which is physics simulations. But the stuff that sits in the middle, where you're doing the black box modeling, off of the featureization provided by the physics simulator
Yeah. Yeah.
gives you the generalizability that you're yearning for, which is when I get a new machine, it's not a whole new machine or a part. I'm sorry. It's not a whole new part. The properties of that part are at least in part identified by the physics simulator.
That's great. Yeah.
What the network is doing is it's dealing with all the unsimulated parts.
That's right.
I think we're going to start seeing more things like that, which are sort of hybrid models that are built off of some known world model that's sort of, and they're example, I can walk you through some examples, but I think we're seeing that in a few places. And in the work we're doing, that's what we're doing. And I think that can give you the best of both worlds.
That's great. Yeah, I think it's the middle is the uncertain, uncomfortable part, but it's where the best outcomes are going to be reached for sure. Yeah, I agree.
And so Sendhil, we'll turn to Rich and Niamh to weigh in on that. Just to kind of put a point on your comments there, is that will enable what? Like, in other words, what you just described enables, from a practical perspective, what?
Yeah. So Francois' point with her, just let me literally repeat it, which is, oh, we built this ML model that took all of the parts we had and kind of told you which parts to use for an arm picker that did well. And then we get whole new parts coming in. Well, that model went stale really fast. But that's reflective of a deeper challenge, which is the challenge of black box models and ML as a whole is distribution shift. We don't know whether when new things come in Francois and Etienne's case, new parts come in, is that in distribution, meaning though it's like kind of the stuff they've seen, or is that a whole new thing? How are we to know? Who's to know? So that's a problem in ML in any field. So, and similarly, in many fields, there's also the opposite problem, which these guys have, which is, well, fine, if I use a physical model, won't that solve the problem? Well, the physical model is underspecified. So we're stuck between an underspecified model and a model that's not underspecified, but is too specified, is like really locked into this distribution. So the way we bridge that gap and get the benefits of ML, which is what? Like dealing with the underspecified. We don't know the physics of picking stuffed animals out of a box. It's like whatever. The way we get the benefits of that ML gives us, but gets the benefits of physics, which is when 100 new parts show up, or if you guys switch manufacturers of some of your parts and say, well, we used to use these manufacturers, now they're using this other manufacturer, how do you know it all still holds? The way you get that is you build off of the scaffolding of the physical models to, in effect, roughly speaking, give you the featureization of the space. So the ML models are learning how to use these features. Now, that's a very crude way of putting it. And I think it's obviously goofy to do that because you kind of want to let the ML models learn their own bit of world models. But a different way of saying it at a higher level is, how do you join the implicit world model inside of a black box to the explicit world model we have and make sure they're coherent enough with each other that you get the transfer property?
Yeah, it's like symbolic solving versus numerical solving, right? Like on one side, you're like, you know how to understand whatever how the solver operates, and on the other, you don't, but you can't use them interchangeably. So it's super valid point. And where has distribution shift been used before successfully?
This is at the research level. I think what you're starting to see now is people who are in the world models literature, where what they're doing is they're taking a set of problems. Sometimes it's going to sound goofy, but since we're talking about the limit, we're talking like 2 years from now. But right now, it might be something as simple as a map of Manhattan or the game of Othello, where we know the world model, but then we ask, does an RL algorithm learn the model of Othello? So then that was the first set of things. And now the next set of things is, suppose I knew the physical model a bit. So in our work, for example, we're doing with chemistry. I know some of the physical laws of chemistry, but the laws of chemistry are underspecified. How can I build up off of that? So that's the kind of, it's not quite at the level that we're describing here, but that's one place. The other place where you've seen it, but not as developed, but is in a much more mundane, old school literature, which is when you're trying to do supervised learning models on spreadsheet-like data. But that seems like a very simple situation. But part of what you're utterly simple, but you can almost think of the columns of the spreadsheets as the implicit world model that the person who authored the spreadsheet had, because they're saying these variables matter, not this variable minus this squared to the log to the n whatever. That's also a variable in the data set.
Yeah, exactly.
And so those are the two literatures where people have tried to kind of do something like this. Though it's funny, the second one is so old school, it seems like stuck in 2015 or 13, but I think there are insights there and for the same thing.
Yeah, but it's a simpler version of the same problem. If it gets black box, it gets black box, right? So
Yes. So the one word that we're dancing around is regularization. You're ultimately saying put a regularizer in any supervised learning model so that it regularizes back, so that it's given some mild penalty at benefit of training, so that it regularizes towards the physical model. But if the physical model is not good, it shouldn't do it when it's not working, but it should be, you're encouraging it to regularize towards the physical model, in effect.
Let me turn to Rich and then Niamh. Any comments here?
Well, this has all been very interesting. We're talking about one limit is you keep the physical simulation and you leverage that. And that's where you would go. But as I listen to y'all and think about it and what my opinion is, I think my opinion is that in the limit, we will have no physical model at all, no simulation at all. It will be more like the model that we have, which is, oh, if I get my hand in there, I'll be able to pick out the objects, and I mean, I'll be able to move them any place in the space. And so I think there is, we all have a model of the world and how we can manipulate objects, things that we can do, things that would be difficult for us to do, or things that would take us more time or might be difficult. And so that kind of model is, I don't know what to call it. It's a predictive model. It's an empirical model. It's an experiential model. I think that will be where we are at the limit. And that will change things. It'll be much more trial and error. Like as I was listening to this, I started to wonder, why is it all design and then the customer orders things? And instead, why isn't there a hand? Why doesn't Vention have a space where people can try their designs physically? Like, maybe there's a standard robot arm and it can try picking things up. I guess you wouldn't have the parts even. You wouldn't have the teddy bears or the packages that are used.
yeah, the hardware is always such a limit to getting to the outcome, right? The more we can virtualize, the better off we are. And of course, there are things that are very difficult to virtualize, right? That's why there's like tons of multi-physics simulator for simulating all kinds of different stuff, right?
The more you can virtualize.
We've explored things like having a machine that people can remote in and then, control to do some tests. So that could be interesting to do.
Keep in mind, 50% of Vention order shipped the next day they were ordered, and have yet found an enterprise client or any client that does not value speed, right? And this ability to go from a virtual to the physical is one of the reasons we took the Lego approach, because in that hyper speed world that we live in, we simply don't have time to go manufacture a custom part for a given machine. We had to Legoify them. And even though we might not need simulation anymore for the act of training the machine, we might still need it simply for giving confidence to the buyer that the machine will behave at the way it's supposed to behave, at least from a kinematics, but not from a dynamic point of view. And it's such an important act of conviction for client to build the conviction that their $300, $400, $2 million, $3 million equipment will accomplish the mission for which it has been designed.
And there's a middle ground where you do all of that, but it's just like a lower limit. The material is delivered, and then the thing can experiment, and maybe it finds a more efficient way to move with its own experimentation. Because if you do it all in simulation, you have to be conservative in a certain sense, because you're going to rely that this has to work. And so you can't really be the most efficient way of assembling.
It's funny, the work we're doing right now with NV blocks and QMotion and QRobo from NVIDIA, which are context aware, 3D aware motion planning systems. It makes us realize how conservative we are when we program robots, because the system, you scan the environment, right? And it'll leverage every tiny bit of space that's available, even if you don't notice. And sometimes we scan areas and there's a gap, there's a hole, and we see the robot literally going for the hole and then diving into the machine. It will leverage every single tiny bit of space that's available by the millimeter. And when we see this, happening in real time, we're like, okay, wow, like we were usually like a foot away from everything when we program everything ourselves. But when an algorithm has context, it uses every tiny bit of space available. So I think this is actually very true. When the machines are more autonomous, they will leverage opportunities in plenty of ways. We already start to see it.
Just before we go to Niamh here, I just want to pick up on Rich's thing. He compared this to people, and he said, you can give me this job or that job or that job, and with my fingers and my arms and my hands, I can figure out how to do that job. And so you can imagine that really, Vention supplies a system with fuzzy specifications. You can think of it like I can have a 25-person factory, a 100-person factory, or 300. Like you can order them in like number of arms and sort of feet of conveyor. And that system is extremely flexible in all the different things it can do. Like today you want it to sort green and red tomatoes, and tomorrow you want it to assemble running shoes. And so I know, like in other words, I know that sounds like blasphemy to a manufacturing expert, but I think where Rich was going was a very high degree of flexibility. In the extreme, if you're very flexible, then why do you need to design it all up front? In other words, you can imagine just having a humanoid walk into your space and that you can give them whatever task. But if we're sitting somewhere between that, what you're sending to your customer is an infrastructure that has very wide range of capabilities. And based on the number of robotic arms and the types of physical space that it's in and amount of conveyor, strength of lifting, so on. But within those broad parameters, it's very flexible of all the things that it can ultimately do. And I know that's not where we are today, but I think that's where Rich was when he was thinking about in the limit, he was thinking about the generalizability of the components.
That's certainly a good direction to be thinking in, maximal flexibility. I was just thinking that generally there will be a shift of turning over more responsibility to the automation, less being pre-designed by the person. And that will start with the pre-designer just specifying goals and the machine's real-time optimizing. But it can go quite far, and there should be interaction between the automation and the goal specification. Pure flexibility, the way AJ is describing, is also interesting. Like you could start with, okay, we will send you over a few, humanoids, and they will start assembling your thing, and then they will realize, oh yeah, you could replace this by a conveyor belt, and I don't actually have to be a humanoid. You can just mount my arm on this table, and then it could do it. And so they're figuring out by doing it. That would be a limit. And then you send the humanoids back, to Venture and Vention, and you just get the table mounted things.
Yeah, the humanoids are cool because they're easy to deploy, right? We've built our world around the human form factor in a certain way, so they're drop-in, right? Just like self-driving cars. But now the problem is some people forget that in automation we build machines because they're better than humans. So humanoids are not going to be good enough for everything, but they're going to be good enough for certain things for sure.
Vention could be like renting out these things that we'll give you a bunch of these humanoids and they will do it. And then as over time they will figure out a way to do it more optimally, so you don't have to spend so much just to make the things. And then Vention would take them back. So it's not that you order 300 something or other. So you just I don't know. It could be a business model.
Let me offer Niamh a chance here, and then after Niamh, we'll just do a very fast lightning round. Rich, Niamh, and Sendhil for final comments.
Thanks, AJ. I have got 2 points, one on the manufacturing and one on the model side. So I think the other element that we've perhaps neglected a bit in this conversation is a parallel rise of cheaper, faster, better 3D printing. And to your point, Etienne, around that fast turnaround cycle from order today, ship tomorrow, to what extent have you extended it also to additive manufacturing or print design of your Lego bricks, or do you still outsource that? And does that also become another RLable environment within your overall system?
Even before Vention, I did a bit of field work in additive and metal, mostly metal powder, 3D printing, and so on. And even if the best technology available out there now, it's dated, it's 10 years, 5 to 10 years old. But the speed at which this operates, it's still very, very slow versus the simple lack of pick, pack, ship. An industrial machine like the one we looked at today has literally 500 components, if not more. So if you think about the sheer printing time of 500 custom parts, and most of those parts are, you take a motor, there's hundreds of thousands of components in the motor itself, right? They all would need. I think there's a limit. I think 3D print will be good for the last mile, and we do that to some extent. And I'll take a very simple problem, but you're designing a robot cell, and there's an enclosure, and you design such a way that the enclosure needs cut out, and so on. Today inside Vention, there's already a tool to kind of automatically generate that panel, so you don't have to create the geometry yourself. And we have now a digital integration with a panel supplier that is right by our factories, and those panels ship the next day, right? So it's not 3D printing, but it's still built to print manufacturings, and there will be other opportunities like this for the last mile parts.
Yeah.
And that's where perhaps 3D print can play, but I doubt it's going to play a big role for the vast majority of part in a Lego-like machine, I would say.
Understood. And the second query was just to kind of unpack a little bit more to the extent to which Gen AI was an inflection point or not. So going back to what Sendhil was saying prior, originally we had supervised learning, and that resulted in overfitting to the specifications. On the other extreme, you had unsupervised and latent representation and generalizability. I think the big inflection for many has been around LLMs trying to fit in that sweet spot. And I assume, again, the multi-modality, the fact that you now have VLA, so vision, language, action, is a huge uplift for you both. But can you unpack a little bit as to how much of a uptick that really was since you've been going since 2016, and then moving forward, are there other modalities you'd bring in? So, for example, especially on the customer service side, or in manufacturing, hands are often occupied. So have you moved to voice activated systems or voice mechanisms and bringing that into the loop as well?
Yeah, I mean, for sure, in our internal operations in tech, we are starting to leverage AI. We're leveraging AI quite a bit for development. Like Sendhil was talking about vibe coding. We do these type of things. We're leveraging different suites of tools. On the control side, we are looking more and more into multimodality for the grasping areas, especially with there's tactile elements that we start to find quite interesting, that go a little bit beyond what can be done with cameras and with depth estimation. So we're looking into this as well. And I think the big uptick we've seen, at least in the last year, to answer that portion of your question, was really in pose estimation, grasp planning, and motion planning with our bin picking and rapid operator system. And we're being opportunistic, in the business as a whole, at places where we see we can safely bring AI to gain productivity and help people. I use AI all the time, every day, and I'm trying to push people to do the same.
30 seconds each, starting with Niamh, and then Rich, and then Sendhil. Any concluding comments in terms of thinking about all this into the future?
Yeah, I think especially as the models move towards continual learning, continuous adaptation, I think that's where you're going to have the biggest flywheel on the frontier side of just every time there's a mistake or an addition or some variation on a theme, it will be automatically fed into the model. And because you've got these deployed everywhere from Lockheed to Lowe's, your hive mind will just enable faster capability than anywhere else.
Thank you, Niamh. Rich?
Well, I'm just struck by how fundamental and long-term this project is. Manufacturing, assembly, it's always going to be super, super important. We can't anticipate all the details and how much it will be small lots and how much it will be bigger lots. So I'm sure we'll have the whole spectrum. But this is not going away. This is a really big deal. It was really good talking to you today.
Thank you, Rich. Sendhil?
Yeah, I only have positive. This is just fantastic. It was super interesting, and I really enjoyed the conversation.
And Sendhil, when you made your comments about generalizability in terms of this stack and the process, And you mentioned early on making things RLable. Was there something here that you heard in the process today that you thought, okay, this is the piece that making this RLable is particularly compelling?
I think for me, it feels like, and Etienne, you've been beating the drum on this. It seems to me like the miracle of what you're doing is we've been pushing you to think about the process problems, but you've been focused on the compatibility problems and the value of having a lot of compatible and just the value of having parts that you can serve. So if I take that thread and take that seriously, for me, I find the most interesting pieces here is actually how do you get more and more manufacturers to play by your rules and come onto your platform seems to me like by far the biggest sort of bend the curve here, because then you really can kind of you're sort of imposing your view on the rest of the system, which it feels like you're in a good position to do.
I might have heard that comment from Ajay in the past, I think.
Well, thank you, everybody. Etienne, Francois, very nice to host you on our first episode of season 2. Sendhil, Niamh, and Rich, thank you very much.
This was great.
Thank you, everybody.
Thank you.
It was great to meet you all.
And that's our show for today. Thanks to Rich Sutton, Sendhil Mullainathan, and Niamh Gavin, and a special thanks to Etienne and Francois of Vention. We posted links to our hosts and guest social media feeds and web pages in the show notes, as well as our podcast webpage. Thanks everyone for listening.
The views, opinions, and information expressed in this podcast are those of the hosts and guests and do not necessarily reflect the official policy or position of Intrepid Growth Partners. This content is for informational purposes only and should not be considered as financial, investment, or legal advice.